This video is going to be about empirical formulas. An empirical formula is the lowest possible whole number ratio of an atom in a compound. When we look at an empirical formula, we're not going to be able to divide the subscripts by a whole number and not end up with a decimal. So if you look at all of these examples here, you'll see that all of these examples listed have a subscript of 1, which means I can't divide both numbers and not get a decimal because 1 is the lowest whole number I can have. Another example of this, though, would be something like C4H9. That number cannot be divided by the same number for both and not end up with a decimal. You can divide 4 by 2, but if you try to divide 9 by 2, you get a decimal point. You can divide 9 by 3, but if you try to divide 4 by 3, you end up with a decimal point. So that would make it an empirical formula. The steps to determine an empirical formula are as follows. First, we're going to determine the number of moles in each element. There's kind of 2 approaches that we will be taking. The first is if we have a percentage. We're just going to assume that that percent stands for grams out of 100 if our sample happened to be 100. That way we can convert it to moles. The other one is if we are actually given grams, we can just convert it to moles right away. So we'll go through and do that part first. When we have a problem as such, we're going to want to figure out what we're given. So we're given 38.43 grams of lead, 17.83 grams of carbon, and 3.74 grams of hydrogen. Now it does give us another number, and that is the total sample. The total sample really only matters if it told us you have lead, carbon, and hydrogen, but only gave us 2 of the numbers. We'll see that in some of our other examples that we do in fact need to use that amount. But for right now, all we need to know is that these are our 3 starting numbers. So the first thing we're going to do is try to get our moles set up. So we know we're starting with lead. So we have 38.43 grams of lead. Now our goal is to convert this to moles using dimensional analysis. To do that, we want to get moles of lead on the bottom to cancel. The number we're going to be putting here is 207.2, which is the molar mass of lead, equal to 1 mole. Then we will calculate, but I'm going to set up all of mine first, and then we'll go through and do our calculations. So next would be for carbon, that is 17.83 grams. And the molar mass of carbon, according to the periodic table, is going to be 12.01 grams. And this is also going to be 1 mole. And then the very last one I need to convert is my hydrogen. And in this case, I have 3.74 grams of hydrogen. Now, sometimes for hydrogen, we will be using the diatomic version of it, but in the case of empirical formula, we want to just use 1.01, not 2.02, because it's not Hobart-Finkel's based on these problems. Okay, and then our goal here is going to be to convert. So I'm going to divide. Here I get, when I divide, 0.18457 moles. And I'm just putting a lot of decimals to make sure I'm not rounding too much. If you keep the numbers in your calculator, it's not a huge deal, but try to give at least 2 to 3 decimals when you're writing these, because for some of them, it can affect your overall answer of what you think you're closer to. All right, so now I have all of my answers. Looking at them and going back to my steps here, this was the first step. I converted everything to mole. The next step then tells me I'm going to divide by the smallest number of moles that I calculated. The goal here is to identify the smallest. So between lead, carbon, and hydrogen, I can see that this is my smallest. So I'm going to go ahead and divide all of my answers by this. Obviously, when I divide lead by itself, I get 1. These numbers are going to be representing the subscripts that would be associated with each element. So at least in the beginning, I'm assuming that the subscript on lead is going to be 1. When I divide carbon, I get a number that is approximately 8. It's not exactly 8, and that's okay. I would say if you're only like a tenth, like a 7.9 or between 8.1, that you can round it to the whole number. I will not give you decimals that are that close to looking like a whole number. So for carbon, we round to 8. And then we get also kind of a 19.96 number here. I'm just going to round that to 20. Now, looking back at the rules, it says if necessary, multiply all ratios to get rid of decimals. All of these rounded pretty easily to a whole number, so we don't need to use that step. So our empirical formula here would be lead with a 1 subscript, which I will not write, C8 and H20. And that is just based on mass and the ratio that they have. So we're going to go try some other problems on the next page here. So I'll go through a few more of these a little faster. Here we have a 15-gram sample found to contain sodium and sulfur. We're going to calculate the empirical formula of this compound. So again, we're given the total sample mass, but it's not really relevant here because I already know both kind of components, so I don't really need to know the total. That is just kind of extra information that I don't need in this case. Same setup as before. We have our first mass, 8.83 grams of sodium. Divide that by the molar mass of sodium found on the periodic table, 22.99 grams per 1 mole. We divide that and we're going to get 0.38408. Then we have sulfur, which is going to be 6.17 grams. 1 mole of sulfur, molar mass 32.07. When I divide here, I get 0.1923 moles. And identifying my smallest, we should see that the smallest here is going to be the sulfur, which means dividing it by itself, I'm expecting that subscript to be a 1. While this subscript, I need to determine when I divide. And here I get that it is pretty much 2, meaning Na2S is my empirical formula here. All right, I'm going to help you set up this one, and then I'll have you try it on your own. So here it says we have a 10.150 gram sample of a compound that has only phosphorus and oxygen. And it says that there is this much phosphorus. So in this case, notice it only gives us one of the 2 amounts. So we do know to start that we have a certain amount of phosphorus. So we can set that up, 4.433 grams of phosphorus. And we can go ahead and kind of look up the molar mass of phosphorus, which is 30.97. But 10.15 is not the other amount for oxygen. That's the total amount. So I have an extra step here. I need to take the total amount minus how much I know phosphorus makes up to figure out how much oxygen I need. And so here I get that the total of oxygen is 5.717. So a lot of times, like I said, you're going to be given the total amount, but it's not always relevant. In this case, we needed to use that. So I'm going to get this one set up for you, and then I'm going to have you try to figure out your smallest. Kind of pause your video and see if you can figure out the numbers we're getting here. So go ahead and calculate your answers. Divide by the smallest. Take a moment and pause, and then play the video. Hopefully you were able to determine that after dividing, phosphorus ended up with the smallest. Dividing both of those numbers, this is the ratio to get. Now, when you divided this oxygen, you would have realized that you ended up with a decimal, one that you could not round to a whole number. It was a little too far away. It was closer to 2.5 than 3. And so in this case, we're pretending for right now that this would be our formula. But hopefully we know we can't have half of an atom, so this isn't going to work. But we can go ahead to try to get rid of it and multiply it by a factor. I'm going to just double it, which will mean I have to double both because I need to keep the same ratio between the elements. And so this is the empirical. And as we know, empirical means I can't divide by any number without getting a decimal. And so that is going to work as an empirical formula. All right, looking at the next example. This one is having us start with percentages. As I mentioned, if we have percentages, we basically just pretend like they are grams. And that our sample size just happens to be 100 grams. It just makes it easy. So I'm going to pause again. I'm going to let you try to do this one on your own, and then I'll put up the work and kind of talk through it. So take a moment and pause the video, and then I will put up the answers. Okay, here is the answer for number 3. If you wrote your elements in a different order, for example, if you put SO3Na2, that's fine. As long as you have matched the correct subscript based on your calculations with the correct element, the order does not actually matter. But I just wrote it in the order that the problem presented it. So Na2SO3 was the empirical formula here. All right, we'll do something similar with this next one. So again, pause the video here and attempt to answer this question, and then we'll go over it. Number 4 was another one where we had to subtract from the total to figure out the other element's gram amount. We were told that there was 4 grams of calcium present, that calcium and bromine were the only elements present, and that 20 grams was the total sample. So because we knew there was 4 grams of calcium, we can subtract to determine that the rest of it, the 16 grams, would have been bromine. And then just like the other ones, we divide by the molar mass on the periodic table to get our decimal in moles and divide by the smallest. In this example, the smallest was calcium. Dividing that by itself, we got 1 for our ratio. And then dividing bromine by that number, we get 2 to give us an empirical formula of CaBr.